So my name is Ulrich Langenbach. I'm talking about a heterogeneous multiprocessing platform for software-defined multi-tiered storage architectures. And originally this presentation should have been given by my colleague Ulrich, which accidentally cannot make it to the States for today. So I jumped in. And the work is a joint work with, together with Xilinx Research based in Ireland. And let's get to the content overview. So at first I will give a little introduction to who we actually are. Then I'll talk about multi-tiered storage needs and why they actually need this deterministic low latency that we can deliver through those architectures, and how this can be done and why this can be done cost efficiently and flexibly. Then a section is about what we actually do and how this performance can be delivered in a single chip solution comprising heterogeneous compute solution that is capable of running also Linux. And in the end, we are going into how we combine these Dataflow architectures for acceleration and offloading, how we use dynamic partial reconfiguration of the reconfigurable parts, and how high-level synthesis could be used for some algorithm acceleration. So let's start with a little overview about Xilinx Research. And Xilinx as itself is quite a large organization, and they are around for such a long time. They were founded in 1984. The figures presented here are from fiscal year 2015, so I think that ended in beginning of 2016, like April. So they are a bit older than a year. Nothing much has changed anyway. The research team we work with is based in Ireland. They basically research applications and architectures, obviously based on FPGAs of Xilinx. They are application driven, and the technology they do is for customers, partners, or internal use. They do also marketing, for example, for trade shows. And Xilinx Electronics is a Xilinx ecosystem partner, and we are an alliance partner since 2011, and we use Linux for a long time and also use the Xilinx flavored Beta Linux since almost the beginning it has come out. Our vision is that we want to enable convergence of software and programmable hardware and to open up the economic realizations on top of that. The mission is to de-risk this adoption of such technologies using heterogeneous compute platforms like MPSoC FPGAs, and therefore we provide some IP and also design services for integration of custom accelerations, for example. To support customers, we provide some IPs that are needed for storage or protocol processing nodes. So we have on the top, we have the protocols that are needed for network interfaces. So we have Ethernet MAX, TCP, IP, and UDP protocol accelerators for multiple speeds. Right now we have 10 and 25 gig available and working on 50 gig line rates. We also support key value store acceleration IP that originates from Xilinx Research Ireland actually, and currently we're working on porting this to now modern available devices. Since quite some time we have some Zeta Storix extensions available for specific devices of Xilinx chips. And yeah, we are a team of design engineers, mostly based in southern Germany, and we do have a facility here in San Jose and support. Yeah, most of our customers are located somewhere in Europe or here in the US in the Bay Area. So the motivation to actually start working on this is that some time ago, not that much time ago, when Flash entered the storage arena, it became clear that the software stack adds a lot of latency to the overall processing time, and when a lot of work has been done to reduce that, now most of it has been reduced with introducing NVMe protocol, for example, and this now we have to move to architectures that actually are able to get more memory into systems and network them together. The other thing is that generally CPU systems kind of don't scale anymore for specific applications. One issue is the von Neumann bottleneck, which is described already in the 1970s and by Backus. And the issue is that every data that has to be processed needs to be moved from memory back and forth all the time. And this is a large issue in those architectures. So this is why one reason why we try to move to Dataflow defined architectures. And the other thing is that single core performance of CPUs kind of reaches an end of scaling. So we have still Moore's law going on. We get more transistors on the top of the line, and the single thread performance just maxes out. The same applies to the maximum frequency used, which is just basically to power limits that can be dissipated within packages. And so to fill in the gap, more logical cores have been added to the dice, but not all the applications can be scaled like that. So basically we move from a sequential processing part that is shown on the left. So a lot of operations are scheduled to be executed by a very few amount of operation units, and we scale it out in space. So everything is done in parallel, it is pipelined, data flows through the system, we have a lot tighter data locality, so working around the von Neumann bottleneck at least very close to the operating ALUs. Yeah, so that's the opportunity we go for. This way we go from the amount of flexibility what we have on top of the diagram, we go low in the lower area to more optimized architectures and circuits. As we do usually in our work face applications that are not done for millions of devices, but usually like thousands. We cannot design specific agent ICs, but go to FPGAs, which is then somehow located almost on the right, but definitely not as efficient as dedicated ASICs could be. To leverage all these different architectural benefits which we get from temporal and spatial computation, we use SoCs that provide both. So this is an example that originates a Xilinx Zynq Ultrascale Plus device. So it has a couple of ARM cores, 64-bit ARM cores that run at about 1.2 gigahertz. And additionally, we have a lot of programmable logic inside the devices that also provide very high-speed interfaces. We have a lot of memory interfaces also on it to have local memory for processing. And this way, we save a lot of power, so we don't need to move around data, and the overall power envelope is quite small. So what could a use case be as storage developers? So a lot of data that is stored right now today is image or video data, And usually you don't just want to store that, you want to process it, and users want to find it, identify single instances of that. And so we come up with kind of an architecture to enhance that and accelerate that. This provides a direct network interface to an MPSoC FPGA that's usually directly fed into the FPGA part, so the programmable logic. Within this, we have reconfigurable processing areas. I just mentioned one here, but this could be more of them. And we could add monitoring as well. And in the end, on the other side, we have the storage attached to it. It's also directly attached to the FPGA part, so also programmable logic. We can add accelerators for that. We can also support other protocols like SATA or SAS. Yeah, that's the basic architecture to do. Yeah, so what we have here is I added now some data that can also flow within the programmable logic. Generally, that's interesting because it doesn't cost time. It costs some area on the device, but there is no deferring of operations and within the reconfigurable processing area. So we just feed back portions of the data that now goes to or comes from the network or goes to the drives. We redirect that or copy that to monitoring parts. And if we use the processing, we may regenerate more content. For example, things that we extracted from data that just flows by. And I'm sorry, somehow this animation came in, which I didn't have in mind before. So that's the slide I wanted to show is, so we have the storage node now, we have some processing inside, so what can we do with it in case of imagining we do store image or video content. So one of the things is that we could automatically extract whilst storing this image some metadata like what's the quality of the picture? Is it a good one? Do we want to store it anyway? Or do we want to recommend somebody to enhance it? For example, getting histogram data out of it and judging based on that about the quality, for example. The data that is extracted, kind of regenerated metadata, we can store this directly in local storage or just report it back to any upper layer application that's running somewhere else on the network. And so we feed it back or forth depending on the application. So we have something similar to do for another processing step we could imagine is, so somebody uploads an image, so even those devices produce quite large images, so we want to have thumbnails and galleries, we want to have smaller versions of that. Maybe we already want to do autocorrections based on previously extracted metrics, like the one before. So that's something that could also be just generated on the fly without stalling storage applications or whatever is needed to be done to store the image itself. So it's just a flyby topology kind of processing, and also here the results are reported back to the network or also stored locally within the devices. Now let's go one step further. Imagine we could have some image classification within these processing part within the FPGA. So now we put in this image and we actually get keywords out of it. Like, okay, there is a group of people on the image. It's an outdoors image, and it might have to do something with Xilinx, as the Xilinx logo might be recognized by the classifier. So this could be interesting for later searches. And also here we can just store it locally or report it back to the network again. So if we already got all those information, we can use this to also support searches. So if we didn't actually report the results of the classifier back to the network, but kept it locally, we have a local index for the images that are stored on our storage array. And so a network interaction can just request for images for specific items that I have. So possibly if we could send a request to the device and tell it to get all the images back that show outdoor group of peoples, for example, and in the end the image is reported back to the requester. So with respect to monitoring, I just mentioned that the monitoring is not interfering with what's going on the data path. So it can be used to maintain simple things like performance counter, which wouldn't be an issue to do on CPUs also. But maybe we want to actually have a look at specific patterns that are going on the data flows. So we have to match that pattern. We have maybe to generate IDs and timestamps for later tracing and correlation of what's going on in the whole system, because usually it's not one storage node in the system, but hundreds of them. And with respect to an application requesting specific data, we don't know before actually having all this data where the request got and why latency is, or where the latency that we see in application originates from. So that's an interesting part, and I will show an example for using this later on. The next thing we do need support for is runtime reprogrammability. As we have this node, we have reconfigurable computation resources on it, and we may change the applications, we may update them during runtime, so we need good support for that in the system. So let's go to architectural concepts. For this, I provide a short recap on what we presented last year here at this conference. So we showed a heterogeneous compute device as a single chip solution with direct network interfaces. You're having full accelerators for all the used protocols. We showed how the performance scales within this application and how the scaling capacity and cost of the hybrid storage subsystem worked out. And we added already some kind of a gray boxes style software-defined services, which we will talk about later in more detail. So let's have a look at the presented solution. Basically, it's building blocks we will reuse for the applications that we show this year too. So we have data coming in via the network and going to storage, for example. And also we have management data coming in, like configuration, administration of space for specific applications in the storage, and so on. And let's start with the first block that data enters in. So that's a TCP/IP full accelerator that is used to interface to the network. It implements everything that is needed to communicate via the standard TCP/IP protocols, and everything that goes out there is then filled into later processing steps. And one is the key value store abstraction layer that handles all the data on top of TCP or UDP. So it parses the packets that come in, do the hash lookups, all the value store access communication to the storage engines that we see on the right here on the image, and reformats the results to send it back over the network. So everything here is a streaming architecture, so there is pipelining in place on block and register level, and states are just manipulated as data parsers. So the demonstration works at 10 gigabit per second, but it has been shown in the paper mentioned below that this actually scales to almost 100 gigabit of performance. So one of the interesting approaches here is that we use a hybrid memory system which actually is capable of using multiple and different storage technologies. So here we use DDR memory and NVMe storage technologies for values, and also the hash table is stored in DDR memory to get shorter access times and for completions they get out. So let's have a look at what happens when requests come into the device. For example, this application implements an memcached service. So you get in the request, you get a block back, and at some point everything's decoded, and the hashes are now looked up, and the corresponding data command to get it from the NVMe drive is submitted. And now we have some time that we don't really know of until the NVMe drive responds to that and fulfills the request with the completion. And until then, we do go on processing with everything what comes next. So this is a fully pipelined approach on the block level. And as soon as we get responses from the NVMe drive, everything goes on smoothly. And during this time, more requests are added to the submission queue. So this result is that in the end we have a very high bandwidth, and we can leverage the full speed of the flash memories, and the overall performance is quite well and also scales quite good. Generally, when we started talking about the imagined outline of the architecture, introduced those application-centric view, and everything that I talked about, the metadata extraction, for example, takes place here in those gray boxes. So basically, these are boxes that a user can fill with application logic that they actually need, and depending on what it should do, is they are located behind the network interface or even between or when we already know what is inside those blocks that need to be processed after the key value store processing. So let's have a closer look at what actually happens in those blocks and what we can already provide as proof of concept implementations for these blocks. At first, one thing is that we designed offload engines for Linux kernel crypto API. I think this morning was a presentation that also got into offloading cryptographic capabilities within storage nodes, and how this could actually help doing secure database processing, as the encrypted data doesn't leave the storage node at all. Then we have a non-intrusive latency analysis that is based on PCIe TLPs. Another one is inline processing with deep convolutional neural networks. I already mentioned the classification that you can do within the data stream that comes in or goes out of the system. And in the end, I will show how actually the partial reconfiguration part is supported by the standard Linux kernel, actually, which has been equipped with a framework for that. So the first part is accelerating the crypto API. So our proof of concept actually can do all those interactions that is needed for the Linux kernel APIs. And it does decryption and encryption. Generally, the same API is used also for compression and decompression. And so the way we added this encryption, we can also add other algorithms. Generally, the need for acceleration is due to the high bandwidth that we have in such systems. And our proof of concept is an open source implementation, and it follows the streaming application architecture. So hardware-wise, this is an XC streaming interface, and it's a very lightweight interface with no real blocking structure in it. And the software-hardware interface are scatter-gather DMAs, which are probably well known as interfaces for accelerators. This application has been generated using high-level synthesis. So basically, the description has been done on a C-level code and automatically translated into RTL by the tool. So this is the architecture, how it is integrated into the Linux kernel. So we have user space applications that actually access those encryption services offered by the kernel. Within the kernel, we have drivers for different providers of the same or different encryption algorithms, or, as I said, compression algorithms. These drivers are prioritized, and based on this priority, the kernel chooses which API to use internally. So the user doesn't actually know about which device actually carries out the processing. And those are queued up, these commands, and transferred into the hardware, and the hardware driver actually interacts with the hardware processing block on the right via some internal infrastructure present in the FPGA. Now let's go to the next example that addresses the monitoring aspects of the applications, so this is offers performance analysis. It can actually it is capable of providing single request latency analysis on a hop-by-hop basis. So this is not an statistical approach, but considers every event that actually happens in this system. So it is completely implemented in hardware, so there is no interaction with any other software, so there is no distortion to actual processing. And we have a clock cycle accuracy, which is in this case about 200 megahertz. So the system that we actually used for applying this method is we have on the left side some workstations or servers. That's actually a bad resolution, sorry. They are connected via an Ethernet network to some of those storage nodes. And now we are channeling or transporting PCI Express traffic across this network, this Ethernet network based on TCP. And to evaluate how this impacts the performance of storage devices attached to the end nodes, we added this monitoring capability. So this is an example application of the system. We have a couple of boards connected to each other. Basically, the most interesting part is the two right ones. I'll just show that. So these two blocks. They are forming a distributed PCI Express switch, which is interconnected by an Ethernet and TCP IP stack. And by doing this, we are enabled to actually distribute the complete PCI Express topology. And at each point, we have inserted these monitor probes, and we can take timestamps of any event that we see. An event is basically a packet flowing or TLP passing by in this topology. So we have a TLP flow here, and usually the endpoint is the master on the right side. So there are DMA engines in the devices that actually carry out the transfers and initiate them. And while these TLPs that are generated on the endpoint flow through the system, we take timestamps, and now we subtract timestamps in a central unit after the experiment, and we can see the delays that are added on a hop-by-hop basis. So this is in form of the table below. This is not really interesting, so we cannot extract some information of it. It's just the raw data that we get. But now we can actually see interactions that, well, we thought about that they should happen, but now we see that they actually happen. So what we do see is added latency due to throttling, because the network interface actually is slower than the PCI Express interfaces. So we are having buffers filling up on this part. And we also have latency that is generated by the host. So basically the red part in the middle of those bars is the host processing latency, or the latency a request takes until it gets fulfilled. So we see some regular structures here that are due to PCI Express protocol and implementation parameters, like number of outstanding transactions, number of outstanding DMA transfers of the DMA engine, and also the number of read requests that can be issued in parallel within the PCI Express tree. These is this grouping factor we see here. So this is all based on very detailed timing information on a TLP level. And if we have an application issue, we can actually pinpoint that throughout the whole system. The other example was inline processing with neural networks. So Xilinx did actually develop a tool to migrate from generally architected CNNs or DNNs to FPGAs, and this tool compiles fully trained networks for FPGAs, delivers on special input parameters an architecture and also a scheduling for those blocks. So we have also here a pipeline that is a block level pipeline. We see this on the lower left part of the graphics. So the single steps are distributed across multiple compute units, compute arrays, as is named in the left top diagram, which shows the data flow through the system. And the whole system is capable of processing streams of images in a row without any interruption, and in the output you just get the classifications corresponding to the inputs. So this can be used within such a system, and here's some results that they presented at the Symposium on FPGAs in 2017, so it's quite current. And one of the most interesting parts is the frames per second per watt, which is shown in the lower area, in the lower graph. So it is actually capable of processing a lot more than other current architectures do. So it's an interesting approach, and well, that's a very fast developing area, but you probably know that anyway. So now we have some applications ready that we could put into such a device. So let me show you how to actually do the scheduling and how to interface with those processing areas on the FPGA part. So we will have a look at how the Linux FPGA framework is actually architected. It has been added last year, I think, to the beginning of this year to the mainline Linux kernel, so it's quite a fresh development. It has been driven by Altera, now Intel engineers. So it basically has an interface to the user space via device trees, and it uses device tree overlays. So every FPGA region on the right side has a node in the device tree, and each time we want to change the logic inside of that, we load another overlay into that. And basically this triggers all the actions that are needed to exchange the logic within the corresponding region. So the details left out here. Let's go to the process, which is more interesting, I think, and how long this actually takes to do. So, as I said, there is a device tree on x86 devices. It is supported, mostly unused. On ARM platforms, it is a must to describe all the devices that are present on the SoCs. And so let's assume there is one present, that's the black one in the middle, and now we want to exchange the actual functionality that is attached to one of those node stubs. So we insert a device tree overlay that's shown on the left side into the device tree, and that now triggers the load of the partial bit stream that is needed for the calculation of AES in this case. The partial reconfiguration is then scheduled within the system, so every logs are checked and the processing region is decoupled and so on, and afterwards the partial reconfiguration was successful. The corresponding platform drivers are loaded by the system on itself, so we don't have to do anything about it. Every information needed for this is part of the device tree overlay, and the device is ready to use now. We implemented that as an example on a Xilinx platform, a ZC706 board. Our partial bit stream was about 6 megabytes in size. And the overall latency, also the whole process from triggering the reconfiguration via the device tree overlay until the driver is loaded and so on, getting a usable system again, was about 140 milliseconds. So you cannot actually do this on a megahertz basis, but I think that's enough to get updates into the field or even change application scopes from time to time if it's needed, or adapt to workload changes. Newer devices get faster anyway, so I think it's the current Zynq Ultrascale Plus devices are about 4 times as fast as this one was. With this, I go to conclusion and outlook part. So we come to an end of this presentation. So basically the conclusion is that we see a trend towards unconventional architectures like those Dataflow engines. We already heard that this morning by this SoftFlash, I think was the name of the project. We see a convergence of networking, storage, and compute, portions of a computer system, and getting computation closer to data. Relying only on standard CPUs is possibly not possible anymore for some of the applications that we need to compute. We demonstrated some key concepts for software-defined services which could be added to storage nodes. We presented an offload engine for Linux kernel crypto API. We showed a proof of concept implementation of latency analysis with great detail for PCIe TLPs in this case. Then we showed how to embed deep convolutional neural networks into such systems, and in the end, this is all of this is possible as those new devices become available and also boards become available to do this. We have most of the IPs in place to do collaboration or in-house development with you, for example, so we're interested in that. And the work is based on a Xilinx Zynq Ultrascale chip that we used, and it has a lot of resources to do, and we haven't filled up yet, so we're interested in adding new applications to this. And that's the last slide, and just shows you the currently available platform, or one available platform for doing storage experiments with FPGAs on it. So it has a lot of interfaces for storage and PCI Express based storage systems like M.2 SSDs. You could put in two of them. We have multiple 100 gig interfaces for Ethernet connectivity or InfiniBand. We have host connectivity to PCI Express, so actually we could build hybrid interfaces that have local connectivity via PCI Express to an x86, for example, a server, and at the same time network interfaces providing the storage also to remote systems. Yeah, on the right time, it's not quite good readable. I think it's an NGFF 8644 connectivity for SAS, SATA, and NVMe interfaces. So that's a lot of interfaces, and we have a lot of RAM, like 32 gigabytes available for local processing. Yeah, provided is this by FIDO Systems, and the Accelerator IPs that were mentioned before are also available, and Linux works, and everything is based and available for your experiments. Yeah, so I conclude this presentation with this, and thank you very much for being here, and yeah, discussion is open, I think. Yep, go ahead.
Of course, heterogeneous can also be GPU or GPU plus FPGA for storage. What's your thoughts or what you've seen in terms of applications that are better for one or the other? What are the trade-offs?
Yeah, the trade-off. So the question was if a GPU would also be interesting to be included in such SoCs, and how I would interpret in case of trade-offs between GPU, CPU, and FPGA. Is this the question? Okay. So I think for now, most applications that we envisaged didn't actually need GPUs, but might benefit from them. So within the SoC that is present on here, there is two GPUs inside. So these standard ARM Mali cores, so they are available. We never experimented with them right now. So for protocol processing, it's not an inner need, but for a image quality judgment, probably is a good idea to use them. On the other hand, you change the architecture, and it's not that Dataflow centric anymore, because you rely on the interconnects and main memory that is attached to the processing system. So I think that's the largest impact that you get. So you have to have a close look on memory bandwidth then. Yeah. Any other questions or ideas?
So this is actually PCIe Gen3 that you were showing on there.
Yeah, so it is possible to run PCI Express Gen 4 on this interface. We haven't done this yet because the Xilinx cores don't do this. So there is no hard macros available for that, but there is third-party IP that will become available to provide that. Yeah. Actually, I'm not sure if you're then... So the Gen 4 by 8 is available with Xilinx IP. Generally, this is a connected X16 connector. So maybe with third-party IP, you can actually have a Gen 4 by X16 connectivity. Yeah. So what we did right now is we tested Gen 3 by X16, and that worked quite well. Yeah. So the other interfaces on top are Gen 3 by 4 for the M.2s.
So about that interface, so how do you see that? I mean, does the main root complex also see that interface, or that's only seen by the Xilinx IP? I mean, in other words, is there a switch inside?
Yes, for now there is no switch inside. So need to put one in there. So currently there is none, but that's one item we are actually investigating to put a switch inside that, so that all those interfaces that provide PCI Express here is also visible to the host system if it is plugged in. Yeah.
And by put the switch there, you mean software, firmware-wise?
Yes, of course. Yeah, that's then implemented in FPGA Fabric. So there is IP available for that from multiple companies, I think. So you can just buy that, generally speaking, and this way you could interface with the whole part. But on the other hand, if you want to use the internal ARMs, then you have a multi-master system which needs non-transparent bridges, and then so that quite generates a complex system. Yeah, but that's possible. Yeah. Anything else? Okay. Thanks.